So, continuing with section 1 here, with ionic bonding, we end up forming ions, and then ions come from gaining or losing valence electrons, and as they do that, they end up with a stable electron arrangement. What that means is that the normal number of electrons is actually not stable, and they end up, unless they're a noble gas that already has a full octet, then they have to gain or lose electrons until they fill up or empty out that outer energy level. The metals tend to lose electrons, and that's because they have low ionization energies, so it's easy to remove an electron. And so then they'll lose one or more of their valence electrons, and losing electrons is going to cause a positive charge. And then they will end up with the same number of valence electrons as the nearest noble gas, and that is the nearest one is going to be the prior noble gas. So you're actually going to go backwards on the periodic table, and then you go backwards far enough, you end up having to go back to the prior row. And so, as I just did sodium as an example a moment ago, sodium has that as its electron arrangement. Well, when it loses one electron and ends up with that, and that electron arrangement happens to equal neon's electron arrangement. However, it is also the electron arrangement of a sodium ion. And it turns out if we take the thing next to sodium, magnesium has 2, 8, 2. Well, it does the same thing. It loses electrons until it gets an octet, which means emptying that out completely. And so then that's magnesium with a 2+ charge, which is also the same as the electron arrangement for neon. And so most elements are trying to get to their noble gas arrangement. It says usually here, because some weird things happen with the transition metals, and we won't get into it much, although we'll touch on it a little bit more if you're in person with me. Here they run through the sodium example. They take the time to write out the number of electrons and protons here, and since there's 10 negatives and 11 positives, then we end up with a result of a 1 positive charge. And notice they are doing the sign after the number. I will point out that a lot of times in chemistry we have invisible ones, and so you're familiar with this. You know the formula of H2O or CO2. Well, if we took the time to write an O there, a C there, there's at least one of them, and so we don't tend to put subscripts with them. Same thing happens here when we have a charged thing. If we don't put a number with it, it's assumed to be 1. Here then is the magnesium example, which I just worked through. I happened to pick the same one that they did. I didn't even really know that that was coming up, but you can take a moment and read both those if you would like. Negative ions tend to be non-metals, and that is the opposite. And so those tend to be the end of the periodic table, the right-hand side, groups 15 through 17. I think I'd lump 14 in there myself, although 14 has those metalloids and down at the bottom some metals. But they tend to have high ionization energies, so it's hard to remove an electron. And in fact, because of their because of that, they have a tendency to, instead of losing electrons, they tend to gain electrons. And if they gain electrons, then that's going to result in a negative charge. And once again, they're going to go until they have a full outer shell. And so if we take chlorine, chlorine has an atomic number of 17, so it had an electron arrangement of this. Well, it's going to be easier for it to gain 1 electron and fill that out. And so then afterwards we have the chloride ion, and the chloride ion has an arrangement of 2, 8, 8, but that also happens to be the arrangement of argon. And that's true for any other nonmetal as well. And so they walk through that same example here. Part of why sodium and chlorine tend to be jumped to as the example of this is because table salt's the common example of this. And then over here they have a table, and in the table they introduce a new term that we haven't mentioned yet. But positively charged ions are called cations, and negatively charged ions are called anions. And you can see the typed version, which is, of course, nicer than my handwriting there. You should know the difference between the two. You're allowed the note card, so feel free to jot it down there. I was taught just silly little drawings. It was a cat with plus signs for the eyes, and that was positive, and then an ant with a negative sign on its body and all these negatively signed legs, that was negative. I've also heard that cats are positive as one as well, and I've seen this one compared to onions as well, because onions smell bad, and then it's really easy to get the anions there. Whatever trick helps you remember it, go for it, or like I said, jot it down on your note card if you want to take up the space. So then this one here arranges them the way they are on the periodic table, and you can see the charges that they end up with. Everything in that first column, the alkali metals, end up with 1+ charges, the alkaline earths. I'll end up with 2+ charges. They only show aluminum here, and that's because we get into some of the metalloids and some strange things happening with post-transition metals. And boron actually is a metalloid, and so we don't show boron. Boron, it turns out, can be a 3+ charge. However, it can be other things as well, and so that's why they exclude it there. But that family didn't really have a name. We didn't give names to these two families either, but you'll notice that everything in the same column has the same charge. This family we did give a name to, the halogens. You'll notice that they put the noble gases over here on this side because they were trying to show what noble gases they were like. But if you look at these, it turns out that nitrogen, oxygen, and fluorine are next to neon, and sodium, magnesium are actually in the next row down. They are behind that, and that goes back to the thing that I was pointing out earlier, that they go to the nearest noble gas, which for them is going backwards, and you go backwards far enough and you end up in the prior row at neon, whereas these things are gaining electrons, and so then they end up at neon that way. And so they can go to wherever the nearest noble gas is, but that going to the nearest noble gas might be backwards to get to it. Anyway, it's not too critical that you know that. The nice thing is there is this pattern on the periodic table, and if you just figure out which column it's in, you can identify what its charge is based off of that. You don't have to go all the way back out to figuring out what was its electron arrangement. Is it going to gain or lose electrons? You know the pattern of how many valence electrons it has on the periodic table already. That pattern then dictates the charges that they're going to end up with. Frequently, there's a great, as usual, there is an example slide here over biology applications. I encourage you to take a moment, pause this, read this before we move into a couple of examples here. So find the symbol of an ion with 16 protons and 18 electrons. Well, the symbol is going to come from the periodic table, and for that we need to know the atomic number. And, as we've mentioned before, atomic number is the number of protons. It's the usual number of electrons, but because this one has changed its number of electrons, we're going to have to base it off of the 16 protons. That tells us that this is sulfur, if you go check your periodic table. Well, now we have 16 positives and 18 negatives. That leaves us with an excess of 18 electrons. I can also see that it gained electrons because 18 is greater than 16. And so then it has 2 more electrons. It's going to give us a 2- charge. Again, I'll take it if you write a -2 charge, but that is not the standard way for a chemist to write it. Anyway, last example here, we're asked to consider calcium and chlorine, and so calcium is a metal and chlorine is a nonmetal. Calcium has 2 valence electrons normally, chlorine has 7 valence electrons, so calcium is going to lose 2 electrons and chlorine is going to gain 1 electron, as we've talked about already, and so then calcium will end up with a 2+ charge and chlorine will end up with a 1- charge. And then they asked us to name these, and we haven't talked about naming yet, but it's real simple. Metals are calcium ion. Ooh, we add the word ion. The nonmetals, there is actually a change. Chlorine, we drop the INE and replace it with D. You may just say, why don't we just replace the N with the D? Well, if you have something like oxygen, it becomes oxide. and so we actually drop the ending and replace it with "-ide." The amount of ending you drop changes on different elements. You'll just get used to hearing it, and I'm not going to penalize you if you spell it wrong, as long as you're close. Online homework might, and so you'll just have to practice and get used to it. You'll hear the names often enough. But anyway, this becomes the chloride, and even though we change the name, we'll still add the word ion. If those two were to bond together, then we drop the word ion and we'd call it calcium chloride. Calcium chloride is sold as an alternative to driveway salt. It's the brand name is the one with the Roadrunner on it, but it lowers the melting point of ice even more, but it's more expensive because it's less common on Earth. Anyway, that finishes up section 1.